Okay, right. This obviously it's a continuation on the subject of high voltage, and now we are going to refer to what is known as cathode processes or processes, specifically looking at secondary effects. Okay, a cathode, it plays an important role in gas discharges by supplying electrons for the initiation. Simply meaning you'll have your two plates. One plate will obviously be at a higher potential relative to the other plate, okay? And then one of these plates will be your cathode, and then electrons or charged particles will be emitted from the cathode in the direction of the anode. In this case, it's a fair assumption to say it's a perpendicular movement, okay? So cathode plays an important role in gas discharges, meaning there's a discharge in gas happening, okay, by supplying electrons for the initiation, okay, whatever that means. We don't know. That's why we are doing this, because hopefully as we are reading, hopefully we will figure this out as we move along, okay. Sustenance and completion of a discharge for the initiation, sustenance and completion of a discharge. So something somewhere, there's a discharge happening and there's an initiation, there's sustenance as well as the completion of this discharge, okay? And it has something to do with electron supplying, okay? Electrons moving away from the cathode relative to the anode, okay? So let's continue reading. Cathode, it plays an important role in gas discharges by supplying electrons for the initiation, the sustenance, as well as the completion of a discharge in a metal under normal conditions. Okay, electrons are not allowed to leave the surface as they are tied together due to the electrostatic force between the electrons and the ions in the lattice. Okay, the energy required to knock out an electron, it forms from a Fermi level, okay, known as the work function, and it is a characteristic of a given material. So obviously different materials, they will have different characteristics or different attributes, okay. And all it says here is the energy required to knock out an electron from a Fermi level is known as the work function and is a characteristic of the given material, okay, right? Simply meaning different materials, they will have different work functions. I mean, that part makes sense, or it should be clear. There are various ways in which this energy can be supplied to release the electron. So essentially speaking, we are talking about anode, cathode, and we are talking about releasing electrons from a given material, and the ability or the energy required to have the ability to knock out an electron from a Fermi level, that is known as your work function. And this work function, it is unique to the type of material. That's what we know up until this point, okay, right? So let's continue reading. Let's continue reading, right? So there is what we call thermionic emission. It means at room temperature, the conduction electrons in the metal do not have sufficient thermal energy to leave the surface. However, if the metals are heated to temperature 1500 Kelvin and above, the electrons will receive energy from the violent thermal lattice in a vibration sufficient to cross the surface barrier and leave the metal. After extensive investigation of electron emission from metals at high temperature, Richardson developed an expression for the saturation current density, J. Okay, as this is the saturation current density function, J subscript S. It was developed by someone named Richardson, okay? Arguably or possibly or probably or most likely another smart guy, okay? Right. We talk about current density. Current density simply meaning current as a function of space. In this case, that space, it's a flat space, it's a flat surface. So essentially speaking, it's surface area, where the various terms have their usual significance. Let a blah 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 blah. Let's assume this is area for now, okay? Yeah, but anyways, it doesn't matter. But yeah, we'll deal with the mathematics at a later stage, not now. The above expression becomes whatever this is, Okay, right, so A, it's just a way of capturing whatever that is, and then you can substitute it in here, and then boom, now you have A. Okay, good for you. Which shows that the saturation current density increases with a decrease in the work function. Remember, our work function is dependent on what? The type of material. Okay, right? And this current density, it also increases in temperature. Okay, substituting the values of M subscript E, K, and H. A is found to be 120 times 10 to the power of 4 A divided by M squared K squared. However, the experimentally obtained value of A is lower than what is predicted by the equation above. The discrepancy is due to the surface imperfection and surface impurities of the metal, the gas present between the electrode affects the thermionic emission, as the gas may be absorbed by the metal and can also damage the electrode surface due to continuous impinging of ions. Also, the work function is observed to be lowered due to thermal expansion of crystal structure. That's what we talk about when we refer to the lattice. Okay, earlier on. Normally, metals with low work function are used as cathode for thermionic emission. Field emission. Now, remember, up here we spoke of thermionic emission, and down here we are now going to talk about what is called field emission. Okay, field emission. If a strong electric field is applied between the electrodes, okay, the effective work function of a cathode decreases and is given by whatever this is. Okay, right, and the saturation current density is then given by whatever this is. Okay, now this is known as the Schottky or the Schottky effect, and it holds good over a wide range of temperature and electric fields. Calculations have shown that at room temperature the total emissions is still low, even when fields of the order of 10 to the power of 5 V divided by Cm are applied. However, if the field is of the order of 10 to the power of 7 V divided by Cm, the emission current has been observed to be much larger than the calculated thermionic value. Okay, this can be explained only through quantum mechanics, as these high surface gradients, the cathode surface barrier, becomes very thin and quantum tunneling of electrons occur, which leads to field emission even at room temperature. Now, the moment they started using the word quantum, okay, that's when we should have stopped. We should have stopped reading right there. Okay, yeah. But anyways, let's continue reading. Electron emission by positive ion and excited atom bombardment. Electrons may be emitted by the bombardment of positive ion on the cathode surface. This is known as secondary emission. In order to effect secondary emission, the positive ion must have energy more than twice the work function of the metal, since one electron will neutralize the bombarding positive ion and the other electron will be released. If W subscript K and W subscript P are the kinetic and potential energies respectively of the positive ion, then for secondary emission to take place, W subscript K plus W subscript P should be equal to or greater than 2 times W. Okay, the electron emission by positive ion is the principal secondary process in the Townsend spark discharge mechanism. Neutral. Okay, let's just see. Right. Neutral excited atoms or molecules, in this case your metastables, incident upon the cathode surfaces are also capable of releasing electron from the surface. Now we'll stop there for now. Yes, let me just reread this last part. The electron emission by positive ion is the principal secondary process in the Townsend spark discharge mechanism. Neutral excited atoms or molecules, in this case your metastables, incident upon the cathode surface are also capable of releasing electron from the surface. Now obviously we are going to do a deeper dive on that, but like I said, for now we are just covering the theoretical aspects. So let's stop there for now.